Welcome to partial fraction decomposition. Take a good look, because I'm never going to write it again. PFD, partial fraction decomposition. You might say, what's partial fraction decomposition? Well, this is the place for you, but not yet. So I want to talk again, not again. You don't know what I've thought earlier today. I'm going to talk about rational functions. Remember, rational functions is just some polynomial over another polynomial. A lot of times we'll say p of x over q of x, where these are polynomials. Now, rational functions pop up all the time. Fractions pop up all the time with ratios. That's the really, really big one in chemistry, biology, economics. Ratios are everywhere, right? What's the concentration of this thing? Or, what's the ratio of these two species in a population? Or, just whatever you want to compare, we use fractions. And a lot of quantities that we might compare are either polynomials or we can model them with polynomials. That's really the more important one, is approximate something with a polynomial function. Okay? And so, I hope you can accept my premise that rational functions are useful. Now, we know the integral of some rational functions, right? We know this, we just use a natural log. We know the integral of something like this. Use the power rule. We know the integral of something like this. Maybe you remember this one. It's arctan, okay? But what about something like this? Now, we could try a u sub, but we need a 2x minus 1 on the top, and we can't make it. We can multiply and divide, but adding and subtracting is not going to help us. So we don't have a way right now to deal with something as simple as this. This looks really simple. A 3x over a nice factorable polynomial, that looks easy. What do we do with this? Well, I'm not going to tell you. Okay? I'm not going to tell you what partial fraction decomposition is either. I mean, I will, but not yet. Not yet. Have a little patience, okay? Let's just do an example problem. You need to know things about fractions and polynomials. We'll do a little warm-up example. Part A. Simplify 1 over x plus 1 plus 2 over x minus 2. What does this have to do with calculus, Jason? Calm down. Calm down. Let's do some algebra. So we can't add these. We need a common denominator. They have no common factors. So the only way to get a common denominator, right, is to multiply the first one by x minus 2 and multiply the second one by x plus 1. And if we do this, notice then they're going to have a common denominator. So that's how we can add these together. So that'll give us x minus 2 divided by x minus 2x plus 1 plus 2 times x plus 1 over, again, x minus 2, x plus 1. Great. Now we can add them together, no problem. When we add them together, we add the numerators together and the bottom stays the same. And let's also distribute while we're at it. Usually the rule of thumb is to keep the denominator factored and to FOIL or distribute the numerator so we can collect like terms and we don't have to factor afterwards. Plus 2x plus 2. The denominator stays the same. Okay. And then minus 2 plus 2, 1x plus 2x. We got 3x over. Interesting. What a coincidence, Jason. This was that example I gave you in the previous page. I said we don't know how to integrate this. Well, if this is equal to that, we know how to integrate this thing on the top. That's what this section's all about. Can you do part A backwards? And it's not as simple as you want it to be. This section is tedious, although it makes a great argument for linear algebra. Okay. After this section, everyone's going to be wanting to take linear algebra, or at least wishing that you took it already, which you can't because Calc 2 is a prereq. But anyway, let's do part B. Let's look at the integral of 3x over x squared minus x minus 2 dx. So this integral I said we can't do yet. We need partial fractions. I haven't exactly said what it is yet. We'll get to that. But I showed you in part A, right? That it's just 1 over the x plus 1. And then plus 2 over the x minus 2. And that these are equivalent. We showed that in part A. Part A, we started with this and we went up to this. Well, if this is true, we know how to do this integral. We could do a u substitution on this first guy with u is x plus 1. du and dx are the same. You could do a u substitution with the second one where u is x minus 2, some other u. You could split this up. You could do it all long, do it all out. For time purposes, I'm not going to spend the time, but this is the absolute value of natural log of x plus 1 plus 2 times the natural log of the absolute value of x minus 2 plus some constant. And that's what we're going to be doing today. This integration is really not what's happening. It's really not the important part of today's videos. The integration part is the easy part. Calc 2 is the easy part here. The hard part is going to be this partial fraction decomposition. Saying, if I start with some fraction like this, some rational function, can I split it up? Can I decompose it? How can we decompose that into separate fractions? Into partial fractions, if you will. And that question of how to go from A to B is what we're spending our time on today. So enjoy. That's what we're doing. And yeah. Hope you're ready for some systems of equations because they're coming.